dear listener. Hello and welcome to the Deep Sleep Science Channel. Settle in, get comfortable, and let your mind gently drift with us. Tonight, we'll be exploring the quiet and profound nature of cold, from the vast stillness of space to the deepest chill found right here on our own world. There is no need to focus, only to listen as we begin our journey. The coldest temperature ever reached in a laboratory is just a fraction of a degree above absolute zero, a state so cold it is measured in nanokelvin. At this level of stillness, the usual rules of physics begin to blur, giving way to the strange and wonderful world of quantum mechanics. In this realm of extreme cold, matter can enter a state known as a Bose-Einstein condensate. Here, individual atoms lose their separate identities and begin to behave as a single, coordinated entity, a collective wave of matter that can be observed on a macroscopic scale. The natural background temperature of the universe itself is a gentle 2.7 Kelvin. This faint, pervasive coolness is the afterglow of the Big Bang, a cosmic microwave background that fills all of space, a quiet reminder of the universe's ancient origins. Any object drifting in the vast, empty darkness of interstellar space, far from the warmth of any star, will slowly cool until it reaches this fundamental banter: temperature. It is the baseline state of the cosmos, the gentle equilibrium of a universe in quiet repose. The coldest known natural place in our solar system is not on a distant planet, but within the permanently shadowed craters near the moon's poles. Here, in perpetual darkness, temperatures can plummet to a staggering 25 Kelvin, colder even than the surface of Pluto. These lunar cold traps are a testament to the power of geometry over distance. By being forever shielded from the sun's rays, these isolated pockets can radiate their heat away into space, achieving a deeper cold than many worlds much farther from our star. On Earth, the coldest officially recorded air temperature was a breathtaking -89, 2 degrees Celsius, measured at the Vostok station in Antarctica. This extreme reading occurred in the heart of the Antarctic Plateau, a place defined by its high elevation, dry air, and long, dark winters. Such a profound cold is not a fleeting event, but the result of a stable and persistent set of conditions. For weeks, under clear skies and with calm winds, the snow-covered surface of the plateau relentlessly radiates its warmth into space, allowing a layer of intensely cold air to build near the ground. Satellite data has detected even colder surface temperatures in small hollows on the East Antarctic Plateau, with readings as low as -98 degrees Celsius. These are not air temperatures, but the temperature of the snow surface itself, radiating heat under the clearest, driest, and calmest atmospheric conditions imaginable. These ephemeral cold pockets form when superchilled air, which is denser than the air around it, drains into shallow depressions in the ice sheet. Here, protected from the wind, the air continues to cool, creating a localized and fleeting zone of extreme cold that pushes the limits of what is naturally possible on Earth. The Boomerang Nebula, located 5,000 light-years away, is the coldest known natural place in the universe, with a temperature of just 1 Kelvin. This extraordinary cold is colder than the cosmic microwave background radiation itself, a feat that defies simple explanation. The nebula is a young, expanding cloud of gas and dust being rapidly ejected from a dying star. As the gas expands, it cools dramatically, a process similar to how a refrigerator uses expanding gas to create cold. This rapid expansion has cooled the nebula to a temperature below the natural background of space. When certain atoms are cooled to just billionths of a degree above absolute zero, they can form a Bose-Einstein condensate. In this exotic state of matter, the atoms lose their individual identities and merge into a single quantum state, behaving like one giant super-atom. This collective behavior allows scientists to observe quantum phenomena, such as wave interference and superposition, on a scale large enough to be seen. The condensate becomes a macroscopic window into the strange and beautiful rules that govern the microscopic world. The coldest oceans on Earth are found in the polar regions, where seawater is in constant contact with ice. The presence of sea ice and massive ice shelves chills the water to its freezing point, which is about -1, 8 degrees Celsius for typical seawater due to the bow. Dissolved salts. This frigid polar water is a critical component of the Earth's climate system. As it becomes colder and denser, it sinks and flows away from the poles, driving a slow, deep ocean circulation that transports heat and nutrients around the entire globe. In the coldest parts of the world, a phenomenon known as diamond dust can occur. These are not real diamonds, but tiny ice crystals that form directly in the air when water vapor sublimates in extremely cold, clear, and calm conditions. As these microscopic crystals float gently in the air, they catch the low-angle sunlight, creating a beautiful, shimmering effect that fills the sky with sparkling light. It is a moment of serene and quiet magic, born from the perfect alignment of cold, moisture, and stillness. Some of the coldest natural temperatures in the solar system occur not on the most distant bodies, but in permanently shadowed regions closer to the sun. Geometry can outweigh distance in determining cold extremes, a counterintuitive result that highlights the importance of illumination patterns. This is because a surface that never sees the sun can continuously radiate its heat away into the cold of deep space. Without any incoming solar energy to balance the loss, these dark craters and hollows can reach and sustain temperatures far lower than sunlit surfaces on more distant worlds. Human technology has produced temperatures far below those found naturally on Earth, reaching levels measured in nanokelvin billionths of a Kelvin. In these ultra-cold laboratories, the quantum world comes alive, revealing behaviors that are completely hidden at everyday temperatures. At these temperatures, atomic motion slows to a near standstill, and the wave-like nature of matter becomes dominant. It is a realm where physicists can manipulate and study the fundamental properties of particles with astonishing precision, exploring the very fabric of reality. Across our world, the deep ocean is a realm of profound and enduring cold, with its waters typically hovering just a few degrees above freezing. Sunlight can only penetrate a short distance into the sea, leaving the vast abyss in a state of perpetual darkness and chill, a silent, stable world far removed from the warmth of the sun. The reason for this deep cold lies at the poles. It is here, in the frigid winter air, that surface water becomes intensely cold and salty, and therefore very dense. This heavy water sinks slowly into the abyss, beginning a centuries-long journey along the ocean floor, carrying the polar chill with it as it circulates throughout the globe. High above the polar regions, the atmosphere organizes itself into a vast, rotating mass of cold air known as the polar vortex. This is not a storm in the conventional sense, but a persistent, large-scale circulation that traps cold air near the poles during the winter months, isolating it from the warmer air of the mid-latitudes. When the vortex is strong and stable, the cold remains contained, leading to relatively milder winter conditions farther south. But if the vortex weakens or is disrupted, it can wobble and stretch, allowing lobes of intensely cold Arctic air to spill southward, bringing with them sudden and crease. Dramatic cold snaps to regions unaccustomed to such deep chill. The coldest regions of our planet provide a living laboratory for understanding conditions on other worlds. The physics of ice, the behavior of gases in extreme cold, and the subtle chemical reactions that occur in frozen environments on Earth offer clues about the processes shaping the surfaces of icy moons and distant planets. By studying how landscapes evolve and how life adapts in Antarctica or the high Arctic, we can develop better models for what to look for on Mars, Europa, or Enceladus. Earth's poles become a familiar reference point for exploring the vast and frigid frontiers of our solar system. Mars, our planetary neighbor, has its own polar regions, capped with layers of water ice and frozen carbon dioxide. These ice caps expand and retreat with the changing Martian seasons, a dynamic process that drives winds and influences the planet's thin atmosphere. Studying these polar layers is like reading a climate history book for another world. The distinct bands of ice and dust record long-term cycles of orbital change and atmospheric shifts, giving us a glimpse into the distant past of a planet that was once very different from the cold desert it is today. Jupiter's moon Europa is a world encased in a shell of water ice, beneath which lies a vast global ocean of liquid water. Though its surface is intensely cold, the ocean is thought to be kept liquid by heat generated from the constant gravitational squeezing and stretching exerted by Chair. Jupiter. This hidden ocean makes Europa one of the most compelling places to search for life beyond Earth. It is a world where two essential ingredients for life, water and energy, may be present, locked away beneath a protective frozen crust, far from the light of the Peen. Sun. Another of our solar system's icy moons, Saturn's Enceladus, is also a place of surprising activity. Plumes of water vapor and ice particles erupt from great fissures in its southern polar region, jetting hundreds of miles out into space. These geysers suggest the presence of a liquid water reservoir beneath the ice, warmed by internal heat. The material in these plumes contains simple organic molecules, offering a tantalizing hint that the building blocks for life might exist within this small, cold, and distant world. Farther out in the solar system, on Saturn's largest moon, Titan, we find a world where the chemistry of life operates at a much colder and slower pace. Here, rivers and lakes of liquid methane carve a landscape shrouded in a thick, nitrogen-rich atmosphere, with temperatures hovering around a frigid -179 degrees Celsius. Titan's environment is a kind of prebiotic chemistry lab on a planetary scale. The complex organic molecules that rain down from its hazy atmosphere could be analogous to the raw materials that led to life on early Earth. But here, the process is held in a state of deep frozen suspension. The dwarf planet Pluto, once thought to be a simple, inert ball of ice and rock, has been revealed as a world of stunning geological diversity and surprising activity. Its surface is a mosaic of different ices, frozen nitrogen, methane, and carbon monoxide, that create vast smooth plains and towering mountains of water. Ice. Even at its incredible distance from the Sun, Pluto is not a static world. There are signs of flowing glaciers of nitrogen ice and a thin atmosphere that changes with its long elliptical orbit. It is a dynamic place, sculpted by a gentle but persistent energy that still shapes its surface in the deep cold. Beyond the orbit of Neptune lies the Kuiper Belt, a vast donut-shaped region of space populated by countless icy bodies. These are the leftover building blocks from the formation of our solar system, preserved in a state of deep freeze for billions of years. Studying these distant objects is like archaeological work on the solar system's origins. Their compositions and orbits hold clues about the early migration of the giant planets and the distribution of water and organic materials that may have eventually seeded worlds like our own. Even farther out, enveloping our entire solar system, is the theoretical Oort cloud. This immense, spherical shell of icy debris, is thought to be the source of long-period comets, and it marks the outermost gravitational boundary of our Sun's influence. The Oort cloud is a place of almost unimaginable cold and darkness, its objects only loosely bound to our Sun, trillions of miles away. It is a silent, vast reservoir of ancient material, a ghostly halo surrounding our small planetary system, waiting for a gravitational nudge to send one be, of its icy wanderers on a long journey inward. The concept of a pole of cold refers to the region in a hemisphere that experiences the lowest winter temperatures. On Earth, there are two such poles, one in Siberia for the northern hemisphere, and one on the high Antarctic plateau for the southern hemisphere. These are not single points, but broad areas where a combination of high latitude, continental interior location, and specific weather patterns consistently produces the most extreme cold. They are the natural refrigerators of our planet, vast domains governed by the relentless loss of heat during the long polar night. Over immense timescales, extreme cold can profoundly reshape landscapes. Physical weathering processes, such as the fracturing of rock by ice, become dominant, while chemical weathering slows to a crawl in the absence of liquid water. In the driest and coldest deserts, wind becomes a powerful erosive force, scouring rock and transporting fine particles across the barren surfaces. These slow, persistent forces work over millennia to create the distinctive, starkly beautiful landforms of the polar regions. Across all of Earth's coldest places, from the high plateaus of Antarctica to the deep basins of Siberia, a shared pattern emerges. These regions are defined by atmospheric stability and extreme dryness, a combination that allows the surface to cool relentlessly. While the specific geography may differ, the underlying physics is the same. Cold, dense air pools in low-lying areas, ocean moderation is minimal, and the reflective, snow-covered surface works in concert with long winter nights to radiate warmth away into the clear, dark sky. The boundary where the ocean, the ice, and the atmosphere meet is one of the most important and dynamic interfaces in the Earth's cold climate system. The extent of sea ice acts as a powerful regulator, influencing both the ocean below and the air above. When sea ice is extensive, it forms an insulating cap that prevents the ocean from releasing its heat, which reinforces the coldness of the air. Conversely, areas of open water can inject enormous amounts of warmth and moisture into the atmosphere, destabilizing cold air masses and dramatically altering local weather patterns. In the vast, cold deserts of the world, erosion is not driven by flowing water, but by wind and the relentless stress of temperature change. Rocks can be slowly broken apart by the immense forces of thermal contraction and expansion, while the wind carries away the resulting fine particles. Because many of the chemical processes that break down rock are slowed or stopped by the cold, these landscapes can preserve features for incredibly long periods. They are environments where time seems to move at a different pace, where the slow, patient work of wind and frost is the primary architect of the land. The coldest reaches of space are not entirely empty, but are sparsely filled with interstellar dust grains. These tiny particles, often coated with a layer of water ice or other frozen molecules, are the raw materials from which new stars and planets will eventually form. In the deep cold between the stars, these dust grains act as tiny meeting places for atoms, allowing simple molecules to form on their surfaces. Over millions of years, these slow, cold chemical reactions build up a reservoir of complex materials that will be incorporated into the next generation of celestial bodies. The term snowball Earth refers to a series of ancient ice ages so severe that our entire planet may have been covered in ice, from the poles to the equator. These events, occurring hundreds of millions of years ago, represent the most extreme cold climates in Earth's history. The evidence for these global glaciations comes from distinctive geological deposits found all over the world, which suggest that glaciers once existed, even in tropical latitudes. Escaping such a deep freeze would have required a massive buildup of volcanic gases in the atmosphere to create an intense greenhouse effect and melt the ice. The rotation of the Earth creates immense atmospheric waves, known as Rossby waves, which play a crucial role in shaping our weather. These slow, meandering waves transport heat from the tropics toward the poles and cold air from the poles toward the tropics. The behavior of these waves is closely linked to the stability of the polar vortex. Changes in the pattern of these waves can cause the vortex to break down, leading to the outbreaks of Arctic air that define severe winter weather in the mid-latitudes. The distribution of continents on Earth plays a significant role in determining how and where cold climates can develop. A large landmass situated over a pole, like Antarctica, allows for the formation of a massive ice sheet and the development of an extremely cold continental climate, isolated from the moderating influence of the ocean. Similarly, an ocean surrounded by land, like the Arctic Ocean, allows for the extensive formation of sea ice, which further chills the region. The specific arrangement of land and sea is a fundamental control on the planet's ability to sustain large-scale cold environments. The cold, dense water that sinks in the polar regions drives a global system of deep ocean currents, often called the global conveyor belt. This slow, powerful circulation transports water around the world, a process that can take 1,000 years to complete a single circuit. This constant, deep ocean movement is a critical regulator of Earth's climate, distributing heat and dissolved gases and nutrients around the planet. It connects the surface to the abyss and the poles to the tropics, acting as the planet's slow, silent, and cold heartbeat. The universe did not begin in a state of cold, but in an unimaginably hot, dense point. In the first moments after the Big Bang, everything was a searing plasma, a chaotic soup of energy and fundamental particles, with no structure and no stillness. As the universe expanded, it also cooled. This expansion stretched the very fabric of space, causing the energy within it to spread out and become more diffuse. Over thousands of years, this cooling process continued, slowly taming the initial fire and allowing the first atoms to begin to take shape. The faint, cool glow of the cosmic microwave background that we observe today has its origins in a specific moment in the early universe, about 380,000 years after the Big Bang. This was the epoch of recombination, a time when the universe had cooled enough for protons and electrons to combine and form the first stable, neutral atoms. Before this moment, the universe was an opaque fog of charged particles that constantly scattered light. But once neutral atoms formed, light was suddenly free to travel unimpeded through space. The cosmic microwave background is the fading echo of that first moment of transparency, a snapshot of the universe as it first became clear. The tiny temperature variations we see in the cosmic microwave background, mere fractions of a degree, are of profound importance. These subtle ripples in the early universe were the seeds from which all cosmic structure grew, the very first hints of a universe that would not be perfectly uniform. These minuscule fluctuations in density represented slightly stronger gravitational fields, which slowly began to pulling matter from the surrounding space. Over hundreds of millions of years, these small seeds grew into the vast filaments, galaxies, and clusters of galaxies that we see scattered across the cosmos today. As the universe continues to expand, it also continues to cool. The stars will eventually exhaust their fuel and die out, becoming cold, dark remnants like white dwarfs and neutron stars. The great galaxies will slowly drift apart, and the cosmos will grow darker and emptier. In the unimaginably distant future, if this expansion continues, the universe may approach a state known as heat death. In this final state, all energy would be spread so thinly that no work could be done, and the temperature would approach absolute zero, leaving behind a silent, uniform, and profoundly cold cosmos. The accelerating expansion of the universe, driven by a mysterious force known as dark energy, is speeding up this cooling process. By pushing galaxies apart at an ever-increasing rate, dark energy ensures that the universe as a whole will become colder, faster than it would otherwise. This cosmic acceleration paints a picture of a future that is not just cold, but also one of increasing isolation. As distant galaxies are pushed beyond our observational horizon, the universe will appear to become emptier and emptier, its fading light stretched into oblivion by the relentless expansion of space itself. Earth's great ice ages are tied to subtle, cyclical changes in our planet's orbit around the Sun. These changes, known as Milankovitch cycles, alter the amount and distribution of solar energy reaching the Earth over long periods, nudging the climate system in and out of glacial periods. These orbital wobbles and shifts are too gentle on their own to cause an ice age, but they act as a pacemaker. They initiate a series of feedbacks, such as changes in ice cover and atmospheric carbon dioxide, that amplify the initial cooling and push the planet's climate across the threshold into a full-blown glacial state. The concentration of greenhouse gases in the atmosphere plays a critical role in amplifying the gentle push of orbital cycles. As the oceans cool, they can absorb more carbon dioxide from the atmosphere, which reduces the greenhouse effect and further cools the planet, allowing ice sheets to grow. Conversely, as the planet warms at the end of an ice age, the oceans release that carbon dioxide back into the air, amplifying the warming and helping to melt the great ice sheets. This natural feedback loop is a key player in the dramatic climate swings of Earth's recent geological past. In the vast cold clouds of gas and dust between the stars, tiny dust grains act as cosmic refrigerators and assembly plants. Over long periods, molecules of water, carbon monoxide, and other gases freeze onto the surfaces of these grains, forming thick mantles of ice. These interstellar ice layers are not just passive coatings. They create a protected environment where further chemical reactions can occur, shielded from the harsh radiation of space. It is here, in the deep cold, that a rich variety of more complex organic molecules begin to form. The rich chemistry that unfolds on the frozen surfaces of interstellar dust grains is a crucial step in the journey toward life. The ice mantles act as catalysts, bringing individual atoms and simple molecules close together and allowing them to combine into more complex structures, like alcohols, ethers, and amino acids. These life precursor molecules, formed in the deep cold of interstellar space, become incorporated into the next generation of stars and planets. They are the raw, organic ingredients that are eventually delivered to new worlds by comets and asteroids, seeding them with the chemical building blocks of life. The comets and asteroids that delivered water and organic materials to the early Earth were born in the cold, outer regions of the solar system. These icy bodies are essentially pristine time capsules, preserving the original chemical makeup of the nebula from which our sun and planets formed. When these celestial wanderers collided with the young Earth, they deposited their cargo of frozen water and complex organic molecules onto its surface. This cosmic delivery system may have played a vital role in creating the conditions necessary for life to emerge, providing the planet with its oceans and a rich inventory of prebiotic chemistry. In the frigid waters of the polar oceans, the formation of sea ice is a gradual and beautiful process. It begins with the appearance of small, needle-like ice crystals known as frazil ice, which give the water a slightly greasy or soupy appearance. As these crystals multiply, they begin to clump together into small, circular plates called pancake ice, which gently jostle against each other in the waves. Eventually, these pancakes freeze together, forming a solid, continuous sheet of pack ice that can stretch for hundreds of miles, transforming the surface of the ocean. High in the Earth's atmosphere, every single snowflake begins its life as a tiny ice crystal forming around a microscopic nucleus. This speck of dust, pollen, or even bacteria provides a surface upon which water vapor can condense and freeze in the cold, supersaturated air. Once this initial seed crystal has formed, it begins its slow, tumbling journey downward. As it falls through different temperature and humidity layers in the clouds, it grows and develops, with new crystals branching out in a process that gives each snowflake its unique and intricate six-sided symmetry. Antarctic ice cores provide an extraordinary record of Earth's past climate and atmosphere, stretching back hundreds of thousands of years. As snow falls and accumulates, it traps tiny bubbles of the surrounding air, which are then buried and preserved as the snow compacts into solid ice. By drilling deep into the ice sheet and extracting these cores, scientists can analyze the ancient air trapped within. This allows them to directly measure past concentrations of greenhouse gases like carbon dioxide and methane, creating a detailed timeline of how our atmosphere has changed over time. Permafrost, the layer of permanently frozen ground found in the coldest regions of the world, forms over many years as the deep chill of long winters penetrates farther and farther into the soil. It exists in areas where the mean annual air temperature remains below freezing for at least 2 consecutive years. This frozen ground is not always solid, but is often a mixture of soil, rock, and ice, binding the landscape together in a solid mass. The presence of permafrost fundamentally shapes Arctic and subarctic ecosystems, influencing everything from soil stability and water drainage to the types of plants that can grow. The planet's axial tilt, or obliquity, changes slowly over long timescales, wobbling back and forth by a few degrees over tens of thousands of years. These gradual shifts can alter the distribution of cold traps, particularly in the polar regions of planets and moons. A change in tilt could potentially expose a permanently shadowed crater to sunlight, causing any trapped ice to sublimate and disappear. Conversely, it could also cast new areas into permanent shadow, creating new cold traps where volatile substances like water ice could accumulate, remain stable for eons. The cold regions of other planetary bodies offer us a window into the conditions that may have existed on early Earth. By studying the chemistry of ice on Mars or the interactions of organic molecules on Titan, scientists can explore how life's precursors behave under low Burl temperature constraints. These distant, frozen worlds are natural laboratories that inform our theories about the limits of habitability and the potential pathways for the origin of life. They help us understand what our own planet may have been like in its infancy, long before life took hold. Cold and icy regions on planetary bodies are often high-priority targets for scientific exploration because they are excellent places to preserve ancient materials. Ice deposits can act as natural time capsules, storing volatile compounds that were delivered billions of years ago by comets and asteroids. Analyzing the composition of this ancient ice can reveal the history of our solar system's formation and the chemical inventory of the early solar nebula. It is a way of directly sampling the past, reading the story of our cosmic origins as it has been written in the ice. Extreme cold can reshape landscapes over long periods by favoring physical weathering processes over chemical ones. The repeated freezing and thawing of water in cracks can exert immense pressure, slowly prying rocks apart and creating distinctive formations. At the same time, the low availability of liquid water and a slow pace of molecular motion limit the effectiveness of many chemical reactions that would normally break down rock. In this way, cold not only sculpts the land, but also preserves it, creating ancient and stable surfaces that change only very slowly with time. Some of the ultra-cold experiments conducted in laboratories today are designed to simulate phenomena that are thought to have occurred in the early universe, such as the spontaneous breaking of symmetry as the cosmos cooled. Quantum gases can be manipulated to act as small, controllable analog models of these vast cosmological processes. In this way, the coldest places created by humans connect the microscopic world of laboratory physics to the grand, sweeping scale of cosmology. By studying the behavior of matter at temperatures just a fraction of a degree above absolute zero, we can gain insights into the fundamental forces that shape Titane, our universe in its very first moments. The remarkable cold of the high Antarctic plateau is made possible by a persistent weather pattern known as a strong temperature inversion. Under clear, calm conditions, the snow-covered surface radiates heat away very efficiently, becoming much colder than the air just a few hundred feet above it. This creates a stable, stratified layer of intensely cold, dense air near the surface, which is then trapped by the warmer air sitting on top of it. This atmospheric lid prevents mixing and allows the surface air to continue to cool, night after night, leading to the most extreme surface temperatures found anywhere on Earth. In the vast, open landscapes of the polar regions, a phenomenon known as katabatic winds can occur. These are powerful, gravity-driven winds that form when cold, dense air builds up over high plateaus and ice sheets. Pulled by gravity, this heavy air begins to flow downhill, accelerating as it is channeled through valleys and over coastal slopes. These winds can be remarkably persistent and can reach hurricane-force speeds, scouring the landscape and playing a major role in shaping the climate of coastal Dar, Antarctica. The high reflectivity of snow and ice, a property known as albedo, is a crucial feedback mechanism in cold climates. A fresh blanket of snow can reflect up to 90% of incoming solar radiation back into space, which prevents the surface from warming and helps to maintain the cold. This effect is a powerful amplifier of climate change. As warming temperatures cause snow and ice to melt, the darker land or ocean surface beneath is exposed. This darker surface absorbs more solar energy, which leads to more warming and more melting in a self-reinforcing cycle. The distribution of continents and oceans on Earth has a fundamental influence on how cold climates are structured. A large landmass situated over a pole like Antarctica provides a stable platform for a massive ice sheet to form, creating a vast region of intense and persistent cold, far from the moderating influence of the ocean. Similarly, an ocean that is nearly enclosed by land, like the Arctic, allows for the extensive formation of sea ice. This ice cover insulates the ocean, trapping its heat and allowing the overlying atmosphere to become much colder than it would otherwise be, shaping the climate of the entire northern hemisphere. The pole of inaccessibility in Antarctica marks the point on the continent that is most distant from any ocean. This extreme remoteness contributes to its intensely cold climate, as it is completely isolated from the moderating influence of warmer maritime air. This concept illustrates a fundamental principle of continental climates. The farther a location is from the ocean, the more extreme its temperature range tends to be. The pole of inaccessibility represents the ultimate expression of this principle, a place defined by its profound isolation in the heart of the coldest continent. The presence of permafrost, or permanently frozen ground, has a dramatic effect on the landscape and hydrology of cold regions. Because the frozen layer is impermeable to water, summer meltwater cannot drain downwards and instead pools on the surface. This leads to the formation of vast wetlands, countless shallow lakes, and meandering rivers, a landscape known as thermokarst. This waterlogged terrain is a defining feature of many Arctic and subarctic environments, a direct consequence of the cold, solid ground that lies just beneath the surface. Even in the coldest inhabited regions, life finds a way, often through the presence of unfrozen groundwater or local hot springs. These features can create small oases of relative warmth and liquid water in an otherwise frozen landscape. These thermal springs are often fed by water that has circulated deep within the Earth's crust, where it is heated by geothermal energy. When this water returns to the surface, it can maintain its warmth even in the face of extreme sub-zero air temperatures, providing a vital lifeline for local prey ecosystems. In the extremely cold and stable air of a polar inversion, sound can behave in unusual ways. The sharp temperature gradient refracts sound waves, sometimes causing them to become trapped near the surface and travel for exceptionally long distances with very tinty, little loss of clarity. This is because the sound waves, which travel faster in the warmer air aloft, are bent back down toward the colder surface. This can create a kind of acoustic duct, making it possible to hear conversations or other sounds from miles away, a strange and beautiful consequence of the quench atmosphere's rigid structure. Extreme cold also bends light, creating a variety of optical effects and mirages. The same strong temperature gradients that affect sound also alter the density of the air, which changes its refractive index and can cause light rays to curve as they pass through. This can lead to objects appearing distorted, floating above the horizon, or even appearing upside down. These atmospheric mirages are a common sight in polar regions, a visual manifestation of the invisible structure of the cold, stable air. The air in the coldest regions of Earth is often extremely dry, in part because the capacity of air to hold water vapor decreases dramatically as the temperature drops. At -40 degrees, the air can hold only a tiny fraction of the moisture it could at room temperature. This dryness has a profound effect on the environment, contributing to the clarity of the sky, which enhances radiative cooling. It also means that despite the presence of vast amounts of frozen water, the polar regions are often classified as deserts, places where liquid water is incredibly scarce. Cold air is denser than warm air, a simple physical fact that drives many of the large-scale atmospheric phenomena in polar regions. This is why cold air sinks and pools in low-lying areas, and why it forms the powerful katabatic winds that flow down from the high ice sheets. This density difference is also the reason for the formation of stable temperature inversions. A layer of cold, heavy air at the surface simply cannot rise through the warmer, lighter air above it, creating a stable stratification that is the hallmark of the Embraer, coldest, calmest winter nights. The formation of a strong polar vortex is itself a product of the extreme temperature difference between the cold polar regions and the warmer mid-latitudes. This temperature gradient creates a strong pressure difference, which, combined with the rotation of the Earth, sets up the powerful, circling jet stream that defines the edge of the vortex. The vortex acts as a dynamic barrier, a spinning wall of wind that largely contains the frigid polar air. The strength and stability of this wall is a key determinant of winter weather, governing the boundary between the deep cold of the Arctic and the milder climates to the south. The chemistry of the atmosphere is also altered by extreme cold. In the polar stratosphere, at altitudes of 15 to 25 kilometers, the intense cold allows for the formation of polar stratospheric clouds. Beautiful, iridescent clouds made of tiny ice crystals. These clouds, however, play a destructive role. They provide a surface upon which chemical reactions can take place that convert benign forms of chlorine into highly reactive forms. When the sun returns in the spring, this reactive chlorine begins to rapidly destroy ozone, leading to the formation of the Antarctic ozone hole. On Mars, the seasonal freezing and thawing of carbon dioxide at the poles drives a unique form of erosion. As the spring sun warms the ice, trapped carbon dioxide gas beneath the surface builds up pressure and is released in powerful jets that erupt through the overlying ice. These jets carry dark sand and dust from beneath the ice and deposit it on the surface in distinctive fan-shaped patterns. This process, driven by the seasonal cycle of cold and warmth, is a major agent of geological change on the Martian surface today. The cold, permanently shadowed regions of the Moon and other airless bodies are not just cold, but they also act as extremely effective cold traps. Any volatile molecules, such as water, that happen to land in these areas will become frozen and remain trapped there indefinitely. Because there is no atmosphere to transport heat, the only way these regions can warm up is through direct sunlight. Since they are permanently shadowed, they never receive this energy, and so they remain in a state of perpetual deep freeze, accumulating a frozen record of volatile materials over billions of years. The physical state of nitrogen changes dramatically with temperature, and this has a profound effect on the landscapes of distant, icy worlds like Pluto and Neptune's moon Triton. At the frigid temperatures found on these bodies, nitrogen can exist as a solid, a liquid, or a gas, much like water does on Earth. This allows for a kind of nitrogen-based weather system. We see evidence of glaciers of frozen nitrogen flowing across Pluto's surface and geysers erupting nitrogen gas and dust on Triton. It is a world of familiar geological processes driven by an exotic, superchilled substance. Even in the deepest cold of interstellar space, the laws of thermodynamics still apply. The third law of thermodynamics states that as the temperature of a system approaches absolute zero, its entropy or disorder also approaches a minimum value. This means that at absolute zero, a perfectly crystalline substance would have zero entropy. It would be in a state of perfect order with all its atoms locked into a bowl. Single, well-defined ground state. While reaching absolute zero is physically impossible, the pursuit of ever colder temperatures is a journey toward this ultimate state of quantum stillness and order. The coldest engineered systems, designed for ultra-cold physics experiments, are marvels of insulation and isolation. To reach temperatures of nanokelvin, the experimental apparatus must be shielded from even the tiniest sources of external energy, such as vibrations, stray electromagnetic fields, or cosmic rays. This often involves multiple layers of shielding, active feedback systems to cancel out vibrations, and conducting the experiments in electromagnetically quiet environments. In the world of ultra-cold physics, achieving stillness is just as important as achieving cold. The phenomenon of quantum tunneling allows particles to pass through energy barriers that they would not classically be able to overcome. This effect is independent of temperature and means that even at absolute zero, chemical reactions can still, in theory, occur, albeit at an incredibly slow rate. In the deep gold of interstellar clouds, tunneling is thought to play a role in the formation of some molecules. It represents a fundamental quantum leakiness in the universe, a subtle process that allows for change and chemistry even in the most frozen and seemingly bare, static environments. The concept of heat death of the universe is a theoretical end state, where the cosmos has reached a state of maximum entropy, or disorder. In this scenario, all energy would be evenly distributed throughout space, leaving no temperature gradients to drive any processes. The universe would become a vast, uniform, and static soup of particles at a temperature just fractions of a degree above absolute zero. There would be no stars, no galaxies, and no life, just an endless, silent, and profoundly cold equilibrium. The process by which water transitions from a liquid to a solid is a quiet miracle of molecular self-organization. As water cools, its molecules slow down, and the weak hydrogen bonds between them begin to take hold, guiding them into a highly ordered, crystalline lattice structure. This structure is what we know as ice, and it is less dense than liquid water, which is why ice floats. This unusual property is a consequence of the open hexagonal arrangement of the molecules in the ice crystal, a microscopic architectural detail with profound consequences for life on Earth. Seawater freezes at a lower temperature than freshwater because the dissolved salt ions disrupt the formation of the ice crystal lattice. The salt particles get in the way of the water molecules as they try to align, meaning the water must become even colder before the organizing force of the H-estein. Hydrogen bonds can overcome this interference. This principle, known as freezing point depression, is a general property of solutions. The presence of any dissolved substance will lower the freezing point of a solvent, a simple fact of physical chemistry that governs why the ocean can remain liquid even when the air above it is well below zero. The behavior of materials changes dramatically at cryogenic temperatures. Many metals become stronger and more brittle, while rubbers and plastics can lose their flexibility and shatter like glass. This is because the reduced thermal energy makes it harder for the molecular chains and crystal structures to move and deform. Engineers working with cryogenic systems must carefully select materials that can withstand these changes. Special alloys and composites are often required to maintain structural integrity and prevent catastrophic failure when exposed to the deep cold of liquid nitrogen or helium. In the realm of ultra-cold physics, laser cooling is a technique used to slow down atoms to incredibly low speeds. It works by directing precisely tuned laser light at a cloud of atoms. The atoms absorb photons from the laser beam, and each absorption gives the atom a tiny push, slowing it down. By arranging multiple laser beams to hit the atoms from all directions, scientists can create a kind of optical molasses that damps the motion of the atoms in all 3 dimensions. This process can cool a dilute gas of atoms to temperatures of microkelvin millionths of a degree above absolute zero. After an initial stage of laser cooling, atoms can be cooled even further through a process called evaporative cooling. This is done by holding the cold atoms in a magnetic or optical trap and then slowly lowering the walls of the trap. As the walls are lowered, the most energetic or hottest atoms are able to escape, much like the fastest moving molecules evaporating from a cup of coffee. The atoms that are left behind have a lower average energy, which means the cloud as a whole becomes colder and denser, pushing it ever closer to the quantum realm. Many materials, when cooled to extremely low temperatures, exhibit a remarkable property known as superconductivity. Below a certain critical temperature, their electrical resistance drops to zero, meaning they can conduct electricity with perfect efficiency without any energy loss. Superconducting magnets, which are used in MRI machines and particle accelerators, are a powerful application of this phenomenon. They are able to generate incredibly strong and stable magnetic fields, but they must be kept continuously cold with liquid helium to maintain their superconducting state. Another fascinating quantum effect that occurs at low temperatures is superfluidity. Liquid helium, when cooled below about 2 Kelvin, transforms into a superfluid. a bizarre state of matter with zero viscosity, meaning it can flow without any friction. A superfluid can do things that are impossible for a normal liquid, such as flowing up the sides of a container and down the outside, or seeping through microscopic cracks that would be impenetrable to any other fluid. It is a macroscopic manifestation of the frictionless, collective motion of atoms behaving in perfect quantum unison. Even in the profound stillness of absolute zero, matter is not completely at rest. According to the principles of quantum mechanics, particles are always subject to a minimum amount of motion due to the Heisenberg uncertainty principle. This residual, irreducible energy is known as zero-point energy. This means that even in the coldest possible state, atoms and molecules will always be vibrating or jiggling slightly. The universe is fundamentally restless, with a subtle underlying quantum tremor that can never be completely silenced, even in the deepest imaginable cold. The temperature of an object in space is determined by a delicate balance between the energy it absorbs and the energy it radiates away. An object in sunlight absorbs visible and ultraviolet radiation, which heats it up, while at the same time it radiates energy away in the form of infrared radiation, which cools it down. In a vacuum, where there is no air to transfer heat through convection or conduction, radiation is the only way to exchange energy. An object's final temperature is the point at which these two processes, absorption and emission, come into equilibrium. An object in perpetual shadow will continue to radiate its heat away until it reaches the background temperature of deep space. The specific color or wavelength of infrared radiation that an object emits depends on its temperature. Hotter objects emit more energy and at shorter wavelengths, while colder objects emit less energy and at longer wavelengths. This principle is what allows astronomers to measure the temperature of distant stars and clouds of gas. By analyzing the spectrum of infrared light from a celestial object, scientists can determine its temperature with remarkable accuracy. This technique is fundamental to our understanding of the cosmos, allowing us to take the temperature of everything from the coldest nebulae to the hottest stellar nurseries. The thermal expansion and contraction of materials is a major engineering challenge in environments with extreme temperature swings, such as on the surface of the Moon or in cryogenic systems. As materials cool, they shrink, and this can place enormous stress on joints, seals, and structural components. Designs for spacecraft and polar equipment must account for these changes. This can involve using materials with very low thermal expansion coefficients or incorporating flexible joints and other features that can accommodate the dimensional changes without failing. The efficiency of many chemical reactions is highly dependent on temperature. In general, colder temperatures mean slower reaction rates, because molecules are moving more slowly and have less energy when they collide, making it less likely that a collision will result in a reaction. This is why cold environments can preserve materials so well. The chemical processes that cause decay and degradation are dramatically slowed down, allowing ancient ice, permafrost, and even materials in shadowed lunar B craters to remain almost unchanged for millions or even billions of years. In the strange world of quantum mechanics, a phenomenon known as quantum entanglement can link two or more particles together in such a way that their fates are intertwined, no matter how far apart they are separated. Measuring a property of one particle will instantly influence the corresponding property of the other. Many of the experiments that explore entanglement are conducted at extremely low temperatures. The cold, quiet environment helps to isolate the delicate quantum systems from external noise and interference, making it easier to create and maintain these fragile and mysterious connections. In the cold, rarefied upper atmosphere, the beautiful spectacle of the aurora is born. when energetic particles from the Sun, carried by the solar wind, are funneled along the Earth's magnetic field lines toward the poles, they collide with atoms, molecules of air. These collisions excite the atmospheric gases, kicking their electrons into higher energy levels. As the electrons fall back to their original state, they release this excess energy in the form of light, creating the shimmering, dancing curtains of green, red, and blue that we see as the northern and southern lights. The process of sublimation, where a solid turns directly into a gas without passing through a liquid phase, is common in cold and dry environments. On the surface of Mars or in the high, dry valleys of Antarctica, ice can slowly vanish into the air even when the temperature is always below freezing. This happens because even in a solid, some molecules have enough energy to escape from the surface and enter the gas phase. In a very dry atmosphere, these escaped molecules are quickly carried away, and the process can continue, slowly eroding ice deposits over long periods of chaos. Time. The way that heat moves through a material is known as thermal conductivity. In general, metals are good conductors of heat, while materials like wood, plastic, or trapped air are poor conductors or insulators. At very low temperatures, the thermal conductivity of many materials changes significantly. For some pure metals, conductivity can actually increase at cryogenic temperatures, while for alloys and insulating materials, it generally decreases. Understanding these changes is critical for designing effective cryogenic storage vessels, like Dewar flasks, which use a vacuum and reflective surfaces to minimize all three forms of heat transfer: conduction, convection, and radiation. In the cold abyss of the deep ocean, the pressure is immense, a consequence of the weight of all the water above. This high pressure can have surprising effects on the properties of water and ice. Under certain conditions of high pressure and low temperature, water can form different types of ice, known as high-pressure polymorphs, which have crystal structures and densities that are different from the normal ice we see at the surface. These exotic forms of ice may be common in the interiors of icy moons and planets. Even in the most stable, ultra-cold experimental systems, quantum fluctuations persist. These are tiny, fleeting variations in the amount of energy at a point in space, arising from the fundamental uncertainty of the quantum world. They are a manifestation of zero-point energy. These fluctuations mean that even at absolute zero, matter can never be completely motionless or perfectly ordered. The universe has a built-in, irreducible restlessness, a quantum foam of appearing and disappearing virtual particles that prevents true stillness from ever being achieved. In ultra-cold atomic gases, physicists can create quantum vortices. These are tiny, swirling whirlpools in the quantum fluid, but unlike the vortices in a classical fluid, their rotation is quantized, meaning it can only occur in discrete integer units. The study of these vortices provides a powerful way to understand the properties of superfluids and Bose-Einstein condensates. They are a direct, visible manifestation of the strange, quantized nature of motion in the quantum world. At the heart of all temperature is the motion of atoms and molecules. In a gas, particles fly about randomly, colliding with each other and the walls of their container. In a liquid, they slide past one another, and in a solid, they are locked into a lattice, vibrating in place. Temperature is simply a measure of the average kinetic energy of these microscopic movements. To cool something down is to reduce this motion, to calm the ceaseless dance of its constituent particles. As an object becomes colder, its atoms and molecules vibrate and move more slowly, their world becoming quieter and more still. Absolute zero is the theoretical point at which all this classical motion would cease entirely. The chemical bonds that hold molecules together behave like tiny springs. They can stretch bend and vibrate in specific ways, and the energy of these vibrations is quantized, meaning it can only exist in discrete levels. At room temperature, molecules have enough thermal energy to be vibrating quite energetically. As a substance cools, its molecules lose this vibrational energy, settling down into their lowest energy, or ground, vibrational states. This quieting of molecular motion is a fundamental aspect of cooling at the microscopic level, a settling into a state of greater order and stillness. The speed of sound in a medium is determined by how quickly vibrations can be transmitted from one particle to another. In colder air, molecules are moving more slowly and are slightly closer together, which affects how efficiently they can pass on a vibration. This is why temperature gradients in the air, such as in a strong polar inversion, can bend sound waves. The sound travels at different speeds in the cold and warm layers, causing the wavefront to refract or curve, leading to the strange acoustic effects observed in brain. Polar environments. The absorption of a photon by an atom is a quantum event. For an atom to absorb a photon of light, the photon's energy must precisely match the energy difference between two of the atom's electron energy levels. If the energy doesn't match, the photon will simply pass by. Laser cooling works by exploiting this principle. The laser is tuned to a frequency just slightly below the atom's resonant frequency. Because of the Doppler effect, only atoms moving toward the laser will see the light at the correct frequency to absorb it. Each absorption slows the atom down, selectively breaking the hottest particles in the cloud. When a Bose-Einstein condensate forms, the wave functions of thousands or even millions of individual atoms overlap and merge into a single coherent ET, matter wave. This is a purely quantum mechanical effect, a consequence of the fact that at low enough temperatures, the wave-like nature of the atoms becomes larger than the distance between them. In this state, the atoms lose their individuality and behave as a single quantum entity. It is as if the boundaries between them have dissolved, and they have condensed not in physical space, but in the abstract space of momentum, all occupying the very same key. Ground state. In a superconductor, the electrons, which are normally solitary particles that scatter off impurities and vibrations in the crystal lattice, instead form pairs, known as Cooper pairs. This pairing is mediated by subtle vibrations of the lattice itself, and can only happen at very low temperatures. Once paired, these electron duos can move through the lattice without resistance. They behave as a collective quantum fluid, flowing in unison and bypassing the obstacles that would scatter individual electrons. This coherent, frictionless flow of Cooper pairs is the microscopic origin of superconductivity. The phenomenon of superfluidity in liquid helium is also related to the principles of Bose-Einstein condensation. Helium-4 atoms are bosons, and when cooled below their critical temperature, a fraction of the atoms can condense into the lowest possible energy state, forming a bruise. Superfluid component. This superfluid component can flow without any viscosity, coexisting with the normal fluid component of helium atoms that still have some thermal energy. This two-fluid model helps to explain the bizarre properties of superfluid helium, such as its ability to flow without friction and its incredibly high P. Thermal conductivity. Quantum tunneling is a process where a particle can pass through an energy barrier even if it does not have enough energy to go over it. This is a direct consequence of the wave-like nature of particles in quantum mechanics. The particle's wave function can have a small, non-zero amplitude on the other side of the barrier, meaning there is a finite probability of finding the particle bowl. There. The probability of tunneling depends on the height and width of the barrier, but importantly, it does not depend on temperature. This means that even at absolute zero, quantum tunneling can still allow for chemical reactions and other processes to occur, representing a fundamental limit. The idea of a completely static, frozen universe. The formation of an ice crystal begins at the molecular level. A water molecule, composed of one oxygen atom and two hydrogen atoms, has a slight separation of charge, making it a polar molecule. This polarity allows water molecules to form weak hydrogen bonds with each other. As water cools, these hydrogen bonds guide the molecules into a stable hexagonal lattice. Each molecule forms bonds with four of its neighbors, creating the beautiful and iconic six-sided symmetry that is characteristic of all snowflakes and elder ice crystals. The specific shape of a snowflake is then determined by the precise path it takes through the clouds as it grows. In the extreme cold and near vacuum of interstellar space, chemistry happens on the surfaces of tiny dust grains. Individual atoms and molecules drifting through space can stick to the cold surface of a grain, a process known as accretion. Once on the surface, these particles can migrate around until they encounter other reactive species, allowing for the formation of new, more complex PEDAS molecules. The dust grain acts as a catalyst and a meeting place, facilitating a slow but steady cosmic chemistry that would be impossible in the empty gas phase. The faint glow of the aurora is produced by specific quantum transitions in atoms and molecules of oxygen and nitrogen in the upper atmosphere. When an energetic particle from the solar wind strikes an atmospheric atom, it can knock one of its electrons into a higher, excited energy level. This excited state is unstable, and the electron will quickly fall back to a lower energy level, releasing the excess energy as a photon of light. The specific color of the light is determined by the exact energy difference between the two levels. Green and red light from excited oxygen atoms are responsible for the most common auroral colors. In the process of evaporative cooling, it is always the most energetic particles that escape from the liquid or the atomic trap. This is because these hot particles are moving fast enough to overcome the attractive forces holding them in the system. When they leave, the average kinetic energy of the remaining particles is lowered, which means the temperature of the system drops. This simple statistical process, which works for a puddle of water as well as for a cloud of ultra-cold atoms, is a powerful and fundamental cooling mechanism. In the high, cold polar stratosphere, the surfaces of tiny ice crystals in polar stratospheric clouds act as catalysts for the destruction of ozone. They provide a place for benign forms of chlorine to be converted into highly reactive forms, such as chlorine monoxide. This chemical conversion is a critical step in the formation of the ozone hole. The solid surface of the ice crystal allows reactions to occur that would be extremely slow in the gas phase alone, dramatically accelerating the rate at which ozone is destroyed when sunlight returns in the spring. Even at absolute zero, a quantum system is not truly empty, but is filled with a sea of virtual particles that are constantly popping into and out of existence. These fleeting particles are a manifestation of the point energy of the quantum fields that permeate the universe. These virtual particle fluctuations can have real, measurable effects, such as the Casimir effect, where two uncharged parallel plates in a vacuum will feel a slight attractive force. This force is due to a change in the point energy of the space between the plates, a tangible consequence of the universe's underlying quantum restlessness. The interaction between light and matter is fundamentally a quantum process. When an atom emits a photon, it is transitioning from a higher energy state to a lower one. The energy of the emitted photon is precisely equal to the energy lost by the atom. Similarly, an atom can only absorb a photon if its energy exactly matches the energy required to jump to a higher state. This resonant interaction is the basis for spectroscopy, which allows astronomers to determine the chemical composition and temperature of distant stars by RD, analyzing the specific wavelengths of light they emit and absorb. The property of emissivity describes how efficiently a surface radiates thermal energy. A perfect emitter, known as a blackbody, would be one that absorbs all incoming radiation and emits thermal radiation at the maximum possible rate for its temperature. At the microscopic level, emissivity is related to how well the electrons and atoms in a material can oscillate and generate electromagnetic waves. In cold environments like the surface of the Moon, materials with high emissivity will cool down faster and reach lower temperatures in shadow because they are better at radiating their heat away into space. A temperature inversion represents a state of high atmospheric stability. Because the cold, dense air is at the bottom and the warm, light air is on top, there is no natural tendency for the air to mix vertically. The atmosphere becomes stratified or layered. This stability suppresses turbulence and convection, leading to the exceptionally calm and clear conditions often associated with extreme cold events. It creates a quiet, still world where sound travels in strange ways, and the slow, relentless process of radiative cooling can proceed without interruption. The pressure exerted by a gas is a result of the countless collisions of its constituent particles with the walls of its container. According to the kinetic theory of gases, this pressure is directly proportional to the temperature and the number of particles. As a gas cools, its particles move more slowly, and they collide with the walls less frequently and with less force. This is why the pressure of a gas in a sealed container will decrease as it is cooled down. This direct link between temperature and pressure at the microscopic level is a cornerstone of thermodynamics. The strength of materials is determined by the bonds between their atoms and the integrity of their crystal structure. At very low temperatures, there is less thermal energy available to help the atoms move and rearrange themselves in response to an applied stress. This can make some materials, particularly metals with certain crystal structures, more brittle. Instead of deforming or bending, they are more likely to fracture along planes in their crystal lattice. This loss of ductility is a key consideration in cryogenic engineering. The nucleus of a comet is a mixture of ice, dust, and frozen gases, often described as a dirty snowball. As the comet approaches the Sun, its surface begins to warm and the ices sublimate, turning directly into gas. This escaping gas carries dust with it, forming a vast, glowing atmosphere around the nucleus called a coma, and a long tail that is pushed away from the Sun by the solar, wind and radiation pressure. The entire spectacular display of a comet is driven by the simple process of ice turning to gas under the influence of sunlight. The coldest temperature ever officially recorded on Earth was measured at the Soviet Union's Vostok station in Antarctica on July the 21st, 1983. The thermometer registered a staggering -89, 2 degrees Celsius or -128, 6 degrees Fahrenheit, a benchmark in brass. The history of polar exploration and meteorology. This measurement was taken using a standard alcohol thermometer housed in a Stevenson screen, a louvered white box designed to shield the instrument from direct solar radiation while allowing air to circulate freely. It remains the coldest directly measured air temperature on our planet, a testament to the extreme conditions of the high Antarctic plateau. In recent years, scientists have used satellite instruments to detect even colder temperatures on the Antarctic surface. By analyzing thermal infrared data from NASA Landsat 8 satellite, researchers have been able to identify small hollows in the ice sheet where surface temperatures have dropped as low as -98 degrees Celsius. These are not air temperatures, but measurements of the skin temperature of the snow itself, taken remotely from space. This technique allows for a much broader and more detailed survey of surface cold spots than is possible with ground-based weather stations, revealing a landscape of subtle and extreme temperature variations. The temperature of the cosmic microwave background radiation was first measured with precision by Arno Penzias and Robert Wilson, 1965. Using a large horn antenna at Bell Labs, they detected a faint, persistent microwave signal coming from all directions in the sky, a noise they could not account for. This signal was later identified as the remnant heat from the Big Bang, and its temperature was found to be approximately 3 Kelvin. This discovery provided powerful evidence for the Big Bang theory and earned Penzias and Wilson the Nobel Prize in Physics.